Good afternoon. It's my great pleasure to welcome you to the second lecture in the San Diego celebration of the 2016 Kyoto Prize. The Kyoto Prize Symposium is supported by the Inamori Foundation, and I want to thank Dr. Inamori and the members of the foundation who are here today. Please join me in thanking them for their generosity. The symposium celebrates the recipients of the Kyoto Prize, Japan's highest private award for lifetime achievement. The prize is presented annually in 3 categories: advanced technology, basic sciences, and arts and philosophy. With our colleagues at Point Loma Nazarene University, the University of San Diego, and UCSD, we're proud to bring the Kyoto laureates to our binational region. We're especially grateful to Dr. Inamori and the Inamori Foundation for bringing this extraordinary opportunity to our region. And it is now my pleasure to introduce our Vice President for Research, Dr. Steve Welter.
Thank you and welcome. But before we begin our program, I'd like to recognize several of our esteemed guests today. First, our 2016 Kyoto Prize winner and laureates in advanced technology, Dr. Takeo Kanade. If you would please rise and face the audience. It is also, I want to be sure to acknowledge Dr. Kazuo Inamori, who is the president of the Inamori Foundation, founder and chairman emeritus of Kyocera Corporation, founder and honorary advisor to KDDI Corporation, and also emeritus of Japan Airlines. He's a busy man. Unfortunately, he wasn't able to join us today, but we certainly want to honor him as well. The executive director of the Inamori Foundation, Mr. Shioichi Himono. If you please rise, face the audience. And leading our symposium efforts in the community, we have the chair of the Kyoto Symposium organizer, Mr. David Doyle. Director of the Kyoto Symposium organization, Mr. Rod Lanthorn. Executive Director of the Kyoto Symposium organization, Mr. Dick Davis. And from San Diego State University, I'd like to acknowledge Vice President for Business and Financial Affairs and Chief Financial Officer, Dr. Tom McCarron. Vice President for University Relations and Development and President and CEO of the Campanile Foundation, Ms. Mary Ruth Carlton. I also be sure to want to recognize the extraordinary SDSU graduate students who have received the Inamori fellowships this year. If they could rise briefly. And to go off script just for a second, I want to be sure to acknowledge Melissa Hans, who every year keeps me out of tremendous trouble running this operation, dealing with our issues that they emerge, dealing with my issues that always emerge. So I thank you, Melissa. And now we will see a very special video highlighting Dr. Kanade's lifetime achievements.
Takeo Kanade was born in 1945 in Japan in Hyogo Prefecture, the youngest of 5 brothers. He entered Kyoto University and earned his PhD in electrical engineering. After he became associate professor of Kyoto University Department of Engineering in 1980, Dr. Kanade was invited to become a senior research scientist at Carnegie Mellon University and later became director of the Robotics Institute. Dr. Kanade's keen interest in artificial intelligence led him to study computer-based image recognition. For a human being, it's easy to recognize an image. However, it's very difficult for a computer to do the same. Dr. Kanade established the basic theory for computers to recognize images, developed his research, and created groundbreaking technology. In 1995, his innovative work led to the successful completion of No Hands Across America, a self-driving car that traveled from Washington, D.C. to San Diego, paving the way for the realization of autonomous driving. In 2001, Dr. Conadé worked with CBS Sports to develop a multi-robot camera system that was used to broadcast Super Bowl 35. The system, which CBS calls iVision, produces a surrounding view of interesting and controversial plays, providing a real-time scene from a 360-degree perspective. Dr. Conadé has worked with Carnegie Mellon's Virtualized Reality project to build a fully digital room that can capture events occurring in it by 50 surrounding video cameras. From those videos, we can obtain a sequence of a complete 3D representation of the scene, named 4D representation. Dr. Conadé is continuing his work in computer vision and robotic engineering, both in the US and Japan. He enjoys leisure time with his wife and children. Dr. Conadé's advice for young scientists is, research and development should not be deemed as difficult and serious things. Please be positive and enjoy it.
I also want to acknowledge one other person. We did have the laureate in arts and philosophy who was able to get in here, which is wonderful, and we want to recognize Dr. Martha Craven Nussbaum. So I'm very honored today to be able to introduce the 2016 Kyoto Laureate for Advanced Technology, who's really being honored for his contributions to computer vision, robotics, and the ability to meld the two. You know, for those who are trying to figure out the difference between computer vision and a camera, one way to think about it is that a camera sees the world, but the software recognizes the world. In the same way that our eyes can see things, but it is our brain that interprets or puts them into context. Dr. Takeo Kanade, who is also the UA and Helen Whitaker University professor at Carnegie Mellon University, I think it represents a person who excels in both not only accomplishment, but embracing the spirit and the philosophy of the Kyoto Prize. He was born in Japan in 1945 in Hyogo. He got his PhD in electrical engineering from Kyoto University. He taught at the Kyoto University for a number of years until about 1980, in which case he moved to Carnegie Mellon. He became a professor in 1985, and he was also the director of the Robotics Institutes from 1992 to 2001. He's founding director of the Digital Human Research Center in Japan's National Institute for Industrial Science and Technology in 2001, and he's now started a program where he's co-director of the New Quality of Life Technology Engineering Research Center, which is really an NSF-funded joint program between Carnegie Mellon and the University of Pittsburgh. So the normal academic metrics are publications and those kinds of things. He has 300 publications. He has 20 patents. He's a member of the National Academy of Engineering. He's also a fellow of AAAS, IEEE, the American Association of Artificial Intelligence, and to be frank, the list goes on, to be too numerous to actually go through them all. But I don't really want to use the academic metrics today. What I really want to talk about is his ability to maybe change the world. And if you look at the Kyoto Prize is a gift, not a gift, but it's a prize that is awarded to someone for lifetime accomplishment. It's not for a single event. It's for the ability to impact our society in a significant and consistent way. So if you look at his traditional, or his areas of study over the years, they range from facial recognition and the more subtle features of our faces, the ability to deal with face alignment. He's done motion analysis, tracking specific patches through an environment, and able to condense that data into usable data streams. Extraction of 3D images from 2D information, which is called the origami world. An infomedia project, which is image recognition and location in digital libraries. So you can see the scope of the projects is extraordinary. He also has worked on the Digital Human Research Center in Tokyo, where they have robots mimic human functions. And finally, he's worked on the quality of life, where he's looked at computer-assisted hip replacement. The older I get, the more I like what he's working on. But I'd like to really address a few areas specifically. Most notably, that one of the things that he's known for is autonomous vehicles. In 1985, they developed cars that could sense the freeway, change lanes, avoid obstacles using cameras and sensors. In 1995, you saw the No Hands Across America, which was part of his NAV lab. It went from Pittsburgh to San Diego, so this is a return visit for us, where he went almost 3,000 miles with 98.2, you can see the engineering part, the 98.2% of the time being hands-free. Now, the throttle and the brake were managed by a driver, but the steering was managed, as I understand it, by a system called RALPH, which is the Rapidly Adapting Lateral Position Handler, which sounds a lot like HAL from the movie 2001. He also had a portable navigation system, which he says is plugged into the cigarette lighter. That would not make me very comfortable, but as a portable power source. So just to put this into perspective, nowadays we're talking about driverless cars, but this is 1995. So what was going on in 1995? Remember, PCs had yet to get the Pentium 2 chip. Most monitors in 95 were monochrome. Google did not exist yet, and for the high school students, that's really possible. Hotmail did not exist. Even worse, Pokemon did not exist until I know it's getting tough here. And cell phones had one ringtone. So while what we called a cell phone was really sort of something you drug around with you, he was driving, or had a team driving across the US in a hands-free application. So that's pioneering efforts. The other thing I was going to talk about, sort of very briefly, was when we watch TV now, we take so many things for granted. In almost every sporting event, there's a moment where something's happened. Did they get across the goal line? Did the person step out of bounds? Somehow the narrator of the event starts to talk. The camera seems to come in closer. It starts to pivot as if by magic. Eventually the angle comes in, and you can see where the foot either stepped in or didn't step in. You either groan with agony or you cheer with delight. So either way, half the time you should blame Dr. Conaday. For he was the one who brought together a series of digital cameras that were able to reconstruct an image and put time in there as well so that you can start to visualize things that we couldn't have done in any other way. I'd like to kind of close with something, though. We could focus on the technical achievements, and you could look at his autonomous cars as sort of a triumph in engineering. I want to put it in a slightly different perspective, if I may. So my mother, who recently passed away, lived to 91, but until 88, she drove a car, which was a little frightening. But she drove a car, and when she lost her license, she lost her independence. To some degree, she lost a little bit of her self-value, a little bit of her dignity. At least that's how she felt. So I would posit to you that autonomous cars will do more than just find an easy way to get us to the game. It also will revolutionize the way perhaps our society functions, so that people that are elderly, people like my mother, will be able to achieve control of their life in the same way that maybe someone who's physically challenged can have control of their life. So it's that larger framework we need to put these things in. The Kyoto Prize is intended to be given to those people who care and strive to make a difference. Dr. Conaday last night spoke about his projects, and he brought up two words that I wasn't quite expecting. One was he was talked about his passion for his research. And we don't often think of engineers as passionate people. Now, the truth, though, is you cannot, sorry, Monty, you cannot be passionate, you cannot do the kind of work you do, work the long hours, try to figure out the questions without the passion. The other piece that he brought up was the joy it brought him. For there's true joy in discovery. There's true joy in being impactful. And I think that the Kyoto Prize in many ways embraces both that passion and that joy in serving others. So with that, let me introduce Dr. Conaday, who's both an outstanding engineer, but also a person of passion and joy.
Thank you very much, Steve. That was probably the best introduction that I ever had. Thank you. So let's see, is it on? So, so the idea of today's talk is to share the joy or fun that I had in my research. Indeed, I did a lot of different things, and this is a picture of various areas that I worked on. You see, I worked on mechanical object manipulator design, autonomous vehicles, humanoid, and also helicopter, self-flying helicopter or drone, if you call it today, and also all kinds of computer vision project. But by the way, you see the graph here? You know? Sorry, I'll go back. Graph here. People ask what that is. That is actually, you see the horizontal axis is obviously years, 1980 and so forth. Vertical axis is the degree of my interest. So you see things going up, interest going up and down. In some area, I had interest beginning and die out and never done anything. And in some areas, it went up and then down and then come back and so forth. So I hope that I can share some of those transition of my research activities. Now, of course, when you do this various things, from time to time, you have what I call moment of fame. And probably my biggest moment of fame is iVision at Super Bowl 35. It is the system that gives you a movie matrix-like replay anywhere in the American football field. Have you seen movie Matrix? Good. I haven't seen it. But I was told in its climax, the main character jumps and time is frozen and you see him spin, or you are moving around. Now, do you know how that is made? Movie Matrix is captured by having a camera. As many of these dots are actually cameras, as many as a few hundred surrounding a point in the middle of the studio. And at the middle, actor acts. And one of the camera is ordinary camera, so it actually captures the movie. At the right moment, these cameras take a picture of the character from all the directions at the same time. And then each camera image, these camera images are concatenated. So what happens is that all like this and stop. And then next image is taken from here, which should look like this. Next image from here, which should look like this. Next image from here, look like this. So as a result, you get the feeling as if the time is frozen and you are spinning around him. So idea of iVision is to do the same for the football field. However, in the case of football, number one, field is large. Number two, you cannot preset where the interesting thing will occur. It depends on the game. Therefore, instead of a static camera, we prepare a set of robotic cameras around the stadium, each of which can pan, tilt, zoom, so that at each moment, these cameras look at the right position, and as the play develops, these camera changes the directions so that at each moment, movie matrix setup is there. And so that's the idea of iVision. So we bought robots, and these are Mitsubishi Heavy Industries robot, PA-10. At that time, it cost about $80,000. And high resolution camera and high zoom setup lens, and each set cost about $100,000. So we set up 33 of them. So equipment alone is costed more than $3 million. And they are set around, placed around the second deck of the stadium. And they are connected to control trailer outside the stadium. And actually, I climbed, at the top of the scoreboard. It's scary, windy. And from there to here, the distance is about 150 meters. So you can easily understand how big zoom you need and how precise control you need in order to capture the ball or the player in the middle of the frame. And as I said, they are connected to this trailer. So the cable alone is 500 meters per camera. So in total, cables alone, more than 15-kilometer system. It's a big system, And by the way, the Super Bowl is a big event. At one night, more than $500 million is spent. So whenever I ask questions to CBS people, they first say, Dr. Kanade, you may not know, Super Bowl is $500 million event. So anything you say, they say no. For example, I thought all the power to individual cameras are, taken from outlet. I said, no, you don't understand. Super Bowl is 500, everything is 500. So what happens if somebody trips it? That's not good. Therefore, all the power has to be generated at the station, and even the power should be fed to individual camera system from the central location. So they said, even the whole Tampa power is off, this system is still working. That's what they wanted. And so this is what happened.
Now, during today's coverage of Super Bowl 35, CBS Sports will introduce a new technology called iVision. It provides panoramic coverage similar to the special effects in the hit movie The Matrix.
He's Jim Nantz, famous announcer.
A lot of cameras have been mounted on the scoreboard and all along the upper deck at intervals of 7 degrees. Each camera feeds into one of the 30 specially designed
See, at that time, 2001, the digital recorder was that big. Today, it may be about this size. It looks like this. So this is me when I was young. This is a gigantic robotic system. You have to have a perfect idea of the direction, position of the cameras, and the relationship of the amount of zoom, amount of focus to the command that you give from the computer. And that is one of the hardest jobs. So this is inside the control room.
Here it is. This is an example during the warm-ups taken just a moment ago. The pass from Banks to Davis. Look at the way it can whip around. We're all looking forward to it. By the way, it can be used in history.
So these are superstars, Forber. So that's how it works.
That big lane, so he steps up into it. What always makes it easy for a quarterback is to have a clean line of sight. Watch Trent Dilfer, nice look off, looks to his left, and nobody in front of him. Look at that nice lane. He can see the receiver down the field, and what a throw.
So that's what happened. So anyway, since then, I brag myself to be the only professor that has ever appeared on Super Bowl. And by the way, that was designed. The research development contract between Carnegie Mellon University and CBS had actually explicit clause 6, which says, Professor Takeo Kanade, with his name and title clearly shown, you see my name and title was shown, must appear during the broadcast of Super Bowl for 25 seconds. And you know how much it costs for you to have commercial, Super Bowl? 1 second costs about $100,000. So I was there, 25 seconds. So that was one of the biggest moments of fame that I had. Now, of course, I was also in a movie of Hollywood, Bruce Willis. Do you know Bruce Willis? You know, Die Hard, the guy who never died. I was in his movie. It's a long story, so I won't tell you why, how. But this is, you see, Bruce Willis and me. 2.5 seconds. So that's my moment of fame, probably easiest to see. Now, I'm an engineer and a researcher, and many of you are also probably a researcher and also engineer. Now, when asked, most people say about their wish, their goal. They say to perform good and successful research and development. Probably you would say the same thing too. However, when you're asked, what do you mean by good research? What is good research? It's not easy to actually answer that question. Now, late Professor Alan Newell of Carnegie Mellon, he is a big name. He is a founder of AI and of also cognitive science, and respected by everybody. He said, good science, he uses science, responds to real phenomena or real problems. In other words, he said, good research must solve real existing problems, not concocted problems. 2, good science is in the details, like God is in the details. It's not necessarily the huge, humongous theory or the like. Maybe fairly small things, and that might be the essence of the good science. Also, at the bottom, the real test, whether you're doing good science or not, he said, is whether it makes a difference, positive difference in the society. And I think these 3 characterization of good science is extremely good ones, I think, and everybody at Carnegie Mellon, I think, uses this as a good guiding principle of doing good research, and so do I. And I'd like to use this as the main theme of my talk, and I hope you see that you see throughout my research. Now, when I look at myself, now how then, what is the good way to do good research? And I noticed my experience from my own experience and observation about successful research and development. Usually I found successful ideas are often surprisingly simple or even naively trivial. Have you not had an experience when somebody did a good job or read a good paper and say, oh my gosh, this is such a simple idea, I should have done it, The reason that, and then I say that, however, what is the impediment? What prevents you to come up with such simple and good idea. I claim the impediment to such simple thinking is the I know mentality, also known as expert knowledge. Have you not had the experience when you say something, there are always people say, no, you can't do that. Don't you know the right way of doing this and that? That's not the right way. And they are the expert. Also professor too. People like us, like me, professor, has some inferiority complex that must show that I know better than you do. Therefore, whenever a student says something and say, oh, don't you know that in 1965, so-and-so got the same idea and read his paper, he failed. By saying it, I think that I'm, showing off how much knowledge I have. In other words, I think the expert knowledge tend to prevent you to think very simply. And that's reasonable. Why? Because experts are those people who are taught how to do things when given a problem. Therefore, most of the time, by the way, they have a good right idea, most of the time. I'm not saying experts are bad, experts are good. But at the same time, the fact that they know beforehand sometimes prevents them from thinking better way or new way or simpler way. At the same time, though, you cannot amateur to do the right thing. Reliable execution requires substantive knowledge and skill. For example, very simple thing, autonomous driving. You may think from naivety that when you see the car is going left, the right thing to control is turn the wheel to right. If the car is going right, the right thing is turn wheel. Now, if you write the code to do so, then the car doesn't move straight. It begins to swing. Unless you have the right idea of so-called gain in control theory. Otherwise, the car doesn't go straight. Even this simplest thing, you need a knowledge and skill in order to execute correctly. So I summarize this concept. Think like an amateur, do as an expert. Secret of doing the right, good research. I was so convinced that I even wrote a book on it in Japanese. And it's translated to Korean, Chinese, but never translated to English. Sorry about it. So anyway, so I'm going to use that part of some of the chapters from that book as a part of this talk. So one thing that I always recommend to do the good research is to make a scenario when you do a research. In other words, picture success. What can happen as a result? How and when, where the result will be used. Picture it. Think freely and with fun. Then your story will tend to expand. And also, you are willing to talk about it because it's fun. Then other people can join. Then things are rolling and you have a good time and most likely you succeed the research. And that's the story that I'd like to give. So let's use an example of the things like iVision, which I call it many camera system. Not many camera system, many camera system. The system that uses a large number of cameras. So the idea I was having was this. Can we digitize the dynamic real world into computer in real time, around 1990? So around that time, the concept of virtual reality was very popular. You come up with artificial world and you live in it, or you can experience it and use the various display system like Cave, head-mounted display, and so forth. Now, why people talk about virtual reality, I thought? The reason is they want to do some experiment in that world. Now, in the simulated world, we in the virtual world experiment, you might call it simulation. Why do you want to do that? Because I think there's indeed counter corresponding real reality, and you actually want to do experiment in that world. But it's not easy, or even not, it's not even possible to do that in real world. For example, experiment in the space, experiment in military field area, or experiment of what happens if you dismantle this building and build a new building. You cannot do that by experiment. So you want to do that in the simulated world. Therefore, if that's the case, then I claim that in addition to, or even more than, working on the display from virtual reality to the real reality in which we live, I think isn't it more important, or at least as important, to be able to digitize the real world into simulated world. Because, by the way, real world is where everything starts anyway. Okay, so naturally we thought maybe we should begin to develop a device that can digitize the world, 3D. And at that time, we started working on one of the earliest version of scanning laser rangefinder, sometimes called LADAR instead of radar, LADAR, or LIDAR sometimes called today, that can digitize the real world. The way it works is laser is emitted from the bottom and reflected with the mirror that can spin and nod, and so that it can go all the directions. And the time it takes from the reflected light comes back to the place where it started, you can actually measure distance. And that way you can create a three-dimensional picture of the world. And that system, even in early 90s, could actually digitize under the direct sun. So if you digitize a real building, it looks like this. The top is the amount of light that came back, and bottom is the distance. Darker it is, the farther. Wider means closer. So since I know the three-dimensional distance, then you can create, you understand the three-dimensional shape, structure of the world. So for example, this is the inside of Carnegie Museum, and digitize the inside shape-wise, and you can even digitize the curator who were standing there, and take a picture of the wall and put it on the model, and you can create a three-dimensional display from anywhere you want. And today, by the way, this is very common technology, but remember, this is more than 20 years ago. And at that time, people were doing similar thing on a smaller scale, so I told my students, go big. So they went to Cape Canaveral, and this is a rocket launcher. It's big. An individual floor is the size of the building, and you see the whole structure is three-dimensionally digitized, including the wires and chains and so forth, like this. Okay? So we thought this is a great, device. So we thought that this is a great thing, and then at that time it was a .com time, so we thought we should, make a company. So indeed we did. Indeed, Chancellor Khosla was one of the co-founder of the company, and we had a business plan. First year we sell 5 devices, second year 50, third year 500, fourth year 3 of us are millionaires. That's our business plan. Never successful. We could sell only one unit, just one, that's all. So that was complete failure. The reason was maybe it's too early and it was too expensive. Each unit, our selling price was $300,000, and people were impressed and said, wow, Professor Kanahara, this is a great device. How much is it? $300,000. Well, and nobody bought the device. But anyway, we actually went on to do a service like, digitizing the building, a historical building like this, or even went to Egypt to digitize the King Valley tombs three-dimensionally and so forth. But as a company, no success at all. And we even put similar sensor on a helicopter, which, by the way, can fly by itself. Let me see how we're doing. We had a...
But in real life, away from Hollywood, helicopters...
So
really do
around
play
1995, I had a system
They're used every day.
project,
Douse
the
mountain
autonomous
fire,
helicopter
rescue
project.
people from
This
desperate
is 20 years
situations,
ago.
and help us weave through traffic
This
to
is
and from
Dateline.
work. But now, a research team at Carnegie Mellon University
So that's,
has set its sights on perfecting a different kind of helicopter. One they hope will be used by real cops
a
and
model
rescue
helicopter.
teams to save even more lives. Program coordinator Omid Amidi.
This is Amid Amidi, my student. He speaks better, so he is on Dateline. I wasn't.
Ordinary helicopters are flown by hot-blooded men and women. Amidi's chopper, on the other hand, is controlled by something with a different kind of flash, has no ego, and is definitely more complex. You could say it has all the right stuff. What sets his helicopter apart is that there's no human pilot on board. The robo-chopper, as they call it, instead uses a sophisticated computer and some very high-tech systems to fly. The unmanned chopper doesn't quite have a mind of its own. Flight coordinates have to be programmed into its computer, and once airborne, the computer
Without
activates the
GPS
GPS
too.
and a special vision system.
We put together a perception system or a vision system that can actually...
We
look at
actually
its
developed our own
environment and fly the
computing
helicopter.
system
The two
using
cameras on board
Texas
monitor
Instrument
depth perception,
C40
enabling the chopper to
multiple
fly without
processor.
crashing into anything in its path. They also send images back to the command center. At about $80,000, the 150-pound robo-chopper is quite a bargain compared to normal.
So I have to tell you, this is completely autonomous. All you have to do is hit carry return, it take off, it fly, and it lands.
Very systematically. One of these guys is
So
going
the idea is we
robo-chopper
have
isn't
thousands
strong
of them
enough to hoist a
and
body from
fly
the sea or a mountainside.
and
Big
do
Line
a
decided to put the
survey
robo-chopper to the
or
test to find out
fire
how well it performs
fighting,
while searching for a
things
lost
like
soul.
that. That was
In
my
that case, a
scenario.
very patient mannequin in the red jacket. Plugging in the search route coordinates is the first step. When the computer has the data, the robo-chopper takes off with the GPS and the vision system fully activated.
the coordinates of a point in which he has the victim in view.
The chopper's eyes scanned the ground, processing 60 images per second until it finally locked in on the camper's red jacket. The onboard computer then sends the image to the team's command center. Armed with the camper's whereabouts, a ground team could then bring the person to safety.
So that's the kind of thing that we are doing with the helicopter. So we actually put the laser rangefinder, a small version of it, on helicopter and scan the ground. If you scan the foliage, the wooded area, then you can actually get the three-dimensional structure of that, tree line areas. You see how and so forth, three-dimensionally. Our idea was actually we should have a smaller flying vehicle inside, below the tree line, and then this helicopter flies above it and takes the whole overall picture and send it to small drone that is flying between the trees so that they know the bigger context of the environment. That was a scenario we were thinking at that time. And also we could digitize the whole town three-dimensionally. And the task that we were thinking was to take a three-dimensional scanning of this town today and tomorrow and make us find out the difference, which if there's any for example, dangerous things there. And indeed, we found one trash can moved from one day, from one place to the other. Things like that. It's a good scenario that we worked on. Now, all of these things are great things, but still, it takes time to scan. It takes more than 40 seconds to create a complete three-dimensional environment. That's not fast enough to actually capture dynamic event. For example, people move and for doing that, for digitizing the three-dimensional real-time environment, the system has to work much faster. So we thought maybe the right thing to do to develop real-time video rate stereo machine that can generate three-dimensional picture at the video rate, meaning at least 30 frames per second. So we began to develop camera. A stereo, for example, human has two eyes, two cameras. I thought, well, why two? Human has two cameras, eyes. But I thought the more cameras you have, it's more advantageous. It's obvious to me. So we said, okay, let's have more. So we built a 5-eye camera system that can digitize the three-dimensional world in video at video rate, 30 frames per second, in both, as you see, ordinary color image and depth image. You see, I'm doing like this, so my foot is closer, so wider, and my hand is a little closer, and my body is backward, and the background wall is farther. So you see the distance is clearly captured. And we can do that, as you see, 30 frames per second, 200 by 200, 8-bit distance image. Now, and this is probably one of the earliest video rate stereo machine. Now today, by the way, this cost $3 million to build. And it consumes 5 kilowatts. So when it turned on, whole room is really warm. It used about this size electronic circuit, 13 of them, and used 11 by 11 convolution chip, which is about this big, 21 of them. At that time, it was like that. So once you have that, we thought that if we place that stereo machine here, then I know the shape, meaning how your body shape and face shape and so forth. And also, I know the picture, meaning in color of each pixel. Okay? Therefore, if we have that too, then isn't it obvious by using computer graphics technique to generate a picture when viewed from different angle? Because we know the shape, we know the appearance, therefore we should be able to generate the picture from different angle. That's what computer graphics can do. However, when you do that, then there is a portion that was not visible from original view behind. Okay? Therefore, that portion will have a hole in from the new angle. Okay? So how can you solve that? Don't try to fill it in, I said. Solution, put more cameras. If that is not visible, place a camera that can see that area. If there's more places that is not visible, put more cameras. As many cameras as you want. So this was the idea that we had, that is multi-camera whole scene modeling. So this is surgery. A famous surgeon is doing a surgery. Now, many medical students wants to observe. But now only a few students can go there. And even he's not allowed to be too close to the patient. No, don't worry. We cover the whole surgery room with lots of cameras. You see, these are cameras. And then digitize the whole thing, put it in CD-ROM. See, at that time we didn't have DVD, so CD-ROM. And sell it to medical students. And the medical student can see it from any angle he wants. And if we could do this, by the way, in real time, then we can place millions of students in that room virtually, okay? But that's a real world. So as soon as it's a hallmark of Carnegie Mellon Robotics Institute, as soon as you think, you do. So we actually built one at that time, 51 camera system. Now at that time, all these cameras were analog. Today, the cameras are digital, you see. All you have to do is connect to USB. At that time, there was no such a thing. Individual camera has to be digitized, has to go through so-called digitizer, each of which costs about $8,000 at that time. So if you have about 50 camera, that digitizer alone would have cost $400,000. That's too much. Moreover, the total bandwidth, total number of size of the data that you capture is about 20 gigabyte per second. That's too fast. So what we did was we bought 51 analog videotape recorders, you see. And all of these cameras were so-called synchronized and timestamp. So with that, each frame has a unique label. Therefore, you can tell which frame of the videotape which correspond to this camera was taken at the same time as by this camera and so forth. You can do that. But with this system, of course, once this experiment is over, you have to take one videotape recorder out of tape recorder, put it in digitizer, put it back, put it this, put it back 51 times. Even starting the experiment is quite a bit of task because you have to push 51 start buttons. It's a lot of work. So my students complained, Professor Kanada, you are a robotics professor. You should develop robots to push the buttons. I said, no way. And my students complained, why? I told him, because robots are students a lot more cheaper than robots. So they gladly do their work. And so this is when inside the room, things happens, then we can digitize, create, we call it 4D model, and generate a synthetic cord image from any viewing angle. And you can even go, between players and so forth. And that's sort of around 1995-ish. And this is 2000. And then you can create these things. So I named it virtualized reality because it is not virtual reality. It's a reality which is virtualized. So I call it virtualized reality. And the ultimate goal is to make NBA game virtualized. So the idea is to cover the whole NBA court with a large number of cameras and virtualize it, hopefully in real time, and ship it to your home. And you can see the game from anywhere you want. And if you have big living room, you can actually move around with your head-mount display at the same, anywhere you want. And you can even block Michael Jordan's dunk. Of course, it's easy because he does not know you're blocking. So that was our plan and the concept. So I call it, let's watch the NBA on the court idea. Now, so today, if you look at it that way, multi-camera technology are used everywhere. Entertainment, iVision like sports on stage, large area 3D modeling, multi-aperture camera, they are actually sold today so that you can actually take pictures in such a way that everywhere in focus, and you can change the focus in any way you want afterward, not at the time you take a picture. And security and even microscope is now capable to create a three-dimensional picture by having multiple cameras inside the microscope. By the way, when we wrote the first paper of that 5-camera stereo system, surprisingly, we thought this is the best paper that I thought, one of the best papers that I wrote. Surprisingly, the paper was rejected. Rejected. Can you believe the reason? It said, one of the comment, devices that use this many unnecessary cameras are too expensive to be useful. And it even said people like Takeo Kanade, who has so much research dollars, can develop this system, but no other people would use it, can afford to build and use. Reviewers is supposed to be expert. Now today, when you look back, 5 camera is nothing. 5 cameras are nothing. It's cheap. Cameras are everywhere. And today, as you can see, the systems are everywhere that uses 10 camera, 20 camera, 50 cameras, 100 cameras, lots of them. They exist. Okay? So you see, expert their thinking is limited. Because it's a common sense, by the way, at that time, not to increase the amount of data, visual data, because it takes time, computing time. But today, computing time is cheap, cameras are cheap. So, I always go differently from what people recommend. So, okay, if you say so, I'll go the other way. And we thought we should build bigger one. And we actually aimed at 100,000 camera virtualized engine room, currently 480 camera system. This whole dome is covered with 480 cameras as well as about 30 projection system inside. And when it's big, this big, of course, when you do something inside, it generates about 750 gigabyte per minute. It's a huge system. And I don't know whether it's useful. If you do the confetti inside, then the whole scene can be digitized and you can actually trace them completely. So that's the kind of thing that the whole scenario of multi-camera system, which of course, the iVision is a very small, relatively simple applications of this whole idea. Now, so let's move on to a little different topic. I am going to skip a little bit because I have so much fun in talking. I spent too much time on it. Now, I also like to build real hardware systems. And I did different things, space trustwork crawler, medical surgery systems, and so forth. But probably this autonomous vehicle or land vehicle, and I showed the air vehicle, which is helicopter, but also land vehicle is now what you might call driverless car. We started about 1984. In the beginning, we used this small, the vehicle. But the experiments were very limited because at that time, by the way, the computing was very limited. So it's not easy to get enough computing on a small vehicle like that. So this one actually had licensed VHF channel that actually send video from this one to the computer room of Carnegie Mellon and digitize and then process and generate the command, which is radio sent to this one and then move. So I could actually see what my students were doing without going there, because by watching the TV program, okay, because it was a separate channel that we had. So that was limited. So we thought maybe the right thing to do is actually to build a self-contained system. It's not only the car or robot, but also laboratory. So it has cameras, laser range finder. Also inside, it had several workstations at that time called Sun workstations. We had about 3 or 4 in it. So we had an onboard sensor, onboard computer, and also the most important component is onboard researchers who actually share the fate of the program that they write. And as a result, the reliability of the program went up fairly quickly. So this is how it looked early on. Early on, we were working in the road inside the park next to Carnegie Mellon. In the beginning, it was actually moving so slowly, about 1 centimeter per second. It's barely moving. And then 5 kilometer, 10 kilometer per hour, and then began to venture into suburban roads. And when child shows up, laser rangefinder. At that time, the laser rangefinder was that big. And capture. Of course, that is a setup. That child is a child of a programmer who wrote the program to stop in those dangerous situations. And we began to venture the freeway. And the camera is now small, and we had our own radar system and interface and so forth. And this is the kind of thing that we see, so-called lane following. You see the lane marks are recognized, and the car is in the middle. These are the lane marks, and this is its own understanding where it's moving. It's in the middle. It's a little bit left now, you see, and then come back a little left, and now center. And it's actually automatically trigger the lane change. It also understands the obstacle in front of it by using radar. These red dots are the obstacle that system recognized by using radar system. Green box was by vision. And we also had blind spot checking. See, if the car is a blind spot, then it actually checked that. So we built the car number 1, 2, 3, 4, 5, and this car is the car that went on to No Hands Across America in 1995 from Pittsburgh to San Diego. As Steve explained, 98.2% of the distance was driven by computer vision program. And then we also went on to Los Angeles and met the very famous person, comedian, who is known to be a car enthusiast. That is Jay Leno. You see, we met Jay Leno. This is me, Jay Leno. And this is Todd Yoakum. This is Dean Pomelo. They are the one who actually did the whole work. I was just on the car. And we met Jay Leno. But the reason that we met Jay is that, you know, he always used the news article in his program to make a joke. And this NavLab was used. So one day he used the news article about NavLab and says, here's an article. Thanks to Carnegie Mellon University researchers, for the first time in the world, drivers can now take hands off from the wheel, read newspaper, make up, or drink a cup of coffee. And he said, how come that's a world first? People in Los Angeles have been doing that for a long time. That's his joke. And so it's, okay, we have to show this to him. And that's what we did. And now, of course, you may know after that, this is not my work, but 2007, Carnegie Mellon team led by Dr. Red Whitaker and the team won the competition. And this is complete, 100% driving, even no person at the driver's seat. And as you know, today, you know, all these driving assistance is with us, and autonomous driving is definitely in sight, and you hear lots of news. And of course, a lot more research is needed in order to do a complete, genuine understanding of the whole environment, what other cars are trying to do. See, we guess what other cars are trying to do. Yeah? Now, of course, it's easy if nobody drives. Yeah? If all cars are driven by computer, then car-to-car communication will solve lots of problems that we have today. See? By getting rid of the most dangerous object from the road that are human drivers. So maybe we have to have some social solution toward that. Now, one of the things that I do with Professor Srinivas Narasimhan, who is an extraordinary scientist, is what we call smart headlight. And the basic idea is this. When you drive at night in rain, it's not easy to drive because raindrops are obstacle to your view. They appear to be white dots. Now, if you think hard, this is strange, isn't it? Because the raindrops are made of water. Water is transparent. But water drops are round, means spherical. When things are spherical, like water drops, like lens, when the light hits the round or spherical, then it acts as a lens and reflects lights back to you. That's why raindrops appear to be white in your field of view. Don't you want a headlight with which you don't see raindrops at all, and so that you can drive a rainy night, as if you're driving fine night? Well, solution is easy now, because we learned why the raindrops appear white. That is because your headlight hits the raindrops. Therefore, the solution is this. We change the headlight to a projector, indeed the projector that is over there. And when the rain comes down, we send a light so that the rays of your headlight will not hit the raindrops, only go between the raindrops. Then they go to, reach the background and reflect back to you. Therefore, you won't see raindrops. Obvious solution. Now, you may wonder, Is that possible? It is. Why? Because as I said, raindrops are raindrops. Now to human eye is a very slow device. Raindrops look like streaks, like left. But when you take a picture of raindrops with a much higher or shorter exposure time, like 1 millisecond, they are indeed drops. You see, they appear dots. And luckily, we're talking night, so everything else is dark. So you see, when you take a picture, white things are raindrops. So you can easily tell where in your field of view raindrops are. But you don't know where distance of the raindrops. Now that is the harder part. When you are expert, you like us, you can say, okay, that's difficult. How to do? And then we say, it's almost impossible. However, when you come up with a little different idea, the solution is trivial. You place the projector and camera at the same position. Now, of course, you cannot place them at physically the same position. Therefore, you have half mirror or beam splitter, 45 degrees, so that the light reflect back to kind of folded into the same direction. Okay? Then what happens? In the beginning, you turn on all of the rays very briefly, and quickly take a picture. And you can tell which pixel corresponds to the raindrops, meaning which direction raindrops are, even though you don't know the distance to the raindrops. Okay? As soon as you know it, you turn off the corresponding ray of your projector. Then that ray will no longer hit the raindrops, therefore, that's good. Okay? That's what. Now, in reality, however fast you do, it takes a little time. So therefore, by the time you know where the raindrops are and what to do and control, raindrops will probably move a little bit further. But most likely, they move lower. Okay? Therefore, when you see the raindrops in this direction, the right thing to do is turn off the ray that are a little below where you see. Above, safe. Side or up, little upper, left, most likely safe. Lower left, lower right, who knows? Wind may bring this raindrops this way. So fairly dangerous, okay? So you can actually create the sort of a map of danger of hitting the raindrops. So what you should do is turn on and off your ray inverse proportionally to this probability. And then you'll likely not hit the raindrops. Because you see, the goal is to maximize the percentage of the light that go between the raindrops, not minimize the lights. Because to me, if the goal is minimized, the best solution is turn off headlight. Then no light will hit the raindrops. But that's not a good solution. Okay? So you have to turn on the 100. The goal is percentage. Okay? So what we should do is to build a system that is made of projector, which is exactly that, and camera, and between them computer. So you buy a projector and modify it. These projectors today are made of so-called DMD chip, which are made of a large number of small mirrors, which can be controlled very high speed. And then we need even higher speed, so we modify it. By the way, these projectors are very bright. 4,000 lumens are typical, which is as bright as your car headlight. And then you add camera in front of it with 45-degree beam splitter, put it in the cage, and move it and put it on the car. So we have a new car with a new headlight. When we see rain, you don't see the rain. Of course, it's designed to be that way. Snow, this is artificially generated snow. Okay? Now, probably it takes time for this to be really useful, or it may not be even useful. People may not need. But once we understand this kind of a system, then we can have a lot of different applications. For example, probably the simplest is headlight, high beam, low beam control. When you're driving, especially countryside, you actually want to drive with a high beam because you can see farther. But when you see the incoming car, you have to turn low beam. Why? Because your high beam will hit the driver and makes him blind for a short while. And many of us are actually older than 55 years old, and isn't it scary? The duration of that blindness is 8 times longer than 15 years old younger people. During that time, we're driving completely blind. Okay? So, what should we do? Well, it's easy. All you have to do is turn off the beam which corresponds to the eye to the incoming car's driver. Then he won't see your car high beam at all. You see? That's what you should do. So it should be like this. Turn off. And that's not that difficult, because when you see a big, round, white things coming bigger and bigger, and the distance is between the two is farther and farther, then that must be a car which is coming toward you. So when you see it, then what you do is this side where the driver is, turn off that part. Then you see. To him, our car is just appears to be a low beam. But to you, we are driving high beam. So this car is always high beam to you, always low beam to the incoming car. And of course, today, we know the car knows where to drive, car knows where the bicycle, where is the pedestrian, even quicker than human. Therefore, once they detect it, you can send more lights toward them, or actually draw a driving lane for you. That's handy, especially for a countryside road, which are not marked. So you can actually put it in a smaller way and put it in the inside headlight cage, and it should look like this. By the way, I always tease people who are working on augmented reality and saying that, oh, you say augmented reality, augment Pokemon, when you do this, and then it shows the name, the various things, or the name of the building. It's called augmented reality. And I tease those people who work on it, say, isn't that really augmented reality? I say, no, because if I do this and look at it, nothing there. Reality is not augmented. What you augmented is the display of the reality. So they should have called augmented display of reality. It's a little oversell to call it augmented reality. But this one is genuinely augmented, or even non-augmented. Yeah? So finally, I'd like to talk a little bit about the value of research. And I claim people tend to think the research is to do new things, And new is a value. And I claim newness is not a virtue. Usefulness is. Indeed, there are more new things than old things in the world. Anything you think stupid tend to be new. Tend to be new. So newness is not virtue. Usefulness is. And so the key is formulate carefully focused and concrete problem to be solved. For example, think of a particular problem, say face recognition. Here's a whole range of problem. Face should be recognized in any direction, in any lighting, with the database of the pictures, even the picture of me when I was young. That's a whole range of face recognition problem. Given that, inside of that, there are a subset of very useful, concrete, smaller problems, such as face recognition under good lighting condition, frontal, no sideway, or by face recognition by using many cameras. Okay? Those are subset of the problem. Now, when given this area, some people say, oh, I don't want to work on small problem. I'd like to work big problem, and say, this is what I work. And many grad students want to do that. And they say, no way, that's not a good idea, because it's too difficult to solve. Most likely you won't get a solution in your PhD time, if not lifetime. Okay? So more concentrated. Probably this is a good research. Okay? Now, some people actually try to make a bigger problem. I don't want to work on a small problem, so make it big. But if you look carefully, this definition of the problem does not contain any useful subset as a proper subset. Therefore, you can write a paper on it, but not useful, because it can solve no problem, any problem yet. Okay? Worse than this is, of course, working on this. It's called meaningless problem. So I think the key is solvable and meaningful problem. And this has been, by the way, noticed a long time, including, Einstein basically said that the formulation of the problem is 90% of the problem, 10% is solution, things like that. Now, having said that, in general, however, it's very hard to predict the value of research. And let me give you one example. Tracking problem. When you have one picture and have a pattern, and if that moves, and you want to know how much the pattern moved, it's called tracking problem. Okay? And the way to solve the problem is to crop the pattern and scan in the up image and look for the same pattern. And the solution can be formulated to make this error called SSD, sum of squared difference. In other words, G minus picture of X shifted by U, and if U is correct, these two should be the same. Therefore, this should be 0 or close to 0. Therefore, what we want is to find out U, which makes this EU minimum. Yeah? And we're working on this. This is a very important problem, early 80s. And we're working on it. And then my students, Bruce Lucas, came to me and said, Takeo, we got a great idea. I got a great idea. He said, U usually must be small. Therefore, we can use a Taylor expansion and expand this equation by Taylor expansion and use only up to the first term. Then it's like this. Now, U is outside of this equation. So if you put this in here, then this U, EU, becomes quadratic equation of U. Minimizing quadratic equation, high school students can do. Yeah, you learn how to do quadratic equation, which is like this, and minimum is here. And we know how to do this. high school student can do. Now, of course, this is a two-dimensional problem. It's a little more difficult, but the concept is the same. So you can actually get the explicit solution like this. So Bruce said, Takeo, this is really, this works. And great idea. Let's write a paper. I said, no, to him. No way. And he said, why? I said, Bruce, this is not new, because Taylor expansion has been known for 300 years. And what you did is minimize quadratic equation, which high school student can do. If we write such a paper with my name on, my reputation will be ruined. Therefore, you should not write a paper. And he was persistent. We should write. So I told him, okay, go ahead. But make sure you write a paper, submit to a very obscure place so that nobody will read. And he did. And surprisingly, this paper was the best referenced paper I wrote with more than 10,000 citations. And today, this is used everywhere as the basis of MPEG or, autonomous driving, you name it. Any method, any algorithm that deal with video, motion, uses this program, this theory. I'm glad he was so persistent. So since then, I usually say, when your professor says it's wrong, usually he's wrong. So don't listen to your professor. I think that's the secret. Finally, I think I want to say one thing, and by the way, I'm also using, I'm doing the cell tracking, but I don't think I have time to do that. So finally, I'll skip this part and let me conclude. So let me give you a couple of suggestions, a couple of advice. Do fast. I tell students, if you come up with a good idea, there are at least 2 more people in the world who think the same. Probably more than 2, I think. Therefore, the right thing to do is do fast. So the key is not who said it first. Who said it first is not important. What is important is who gets there first. Second, you have to convince people with your result. Otherwise, your work will never notice, will never make a difference. You see, Dr. Newell said, ultimate goal is to make a difference. In order to make a difference, people have to know your work. People have to use your work. So how to do that? Convince. If it works, it's convincing. It's impossible to convince people with a work that doesn't work. So the key test is, if they ask how your method works, we always like. But if they ask that question, I claim they are not yet convinced. If they are convinced, if they were, they would ask different question. How much is it? Then your work is convincing. And finally, I'd like to close this talk with what late Alan Newell always said, that problems are waiting for you to solve. There are lots of them, and I think it's our joy, our passion, our duty to find them, formulate them correctly, concretely, so that we solve it in a useful manner, and the results are used by other people to make difference in this society. Thank you very much.
Head out. I just want to say, not only was it uplifting, but when he said the part about some of the best ideas are naively trivial, I thought, I've been on fire for 30 years. So thank you all for coming. I think it was a fantastic talk. One more round of applause, please.